Welcome to the next video in the systems programming video series. We've just finished up some assignments, and so now we're moving on to the next batch of readings. This will start off with just the first section of chapter 5 of the textbook Dive into Systems. And here it seems like we're getting into the very low-level computer architecture topics. In this week, we are only discussing chapter 5, section 1. And we're going to skip the rest of the sections. Now that, to some degree, I wish we wouldn't. I kind of want to know that stuff. I could just read the textbook, and just do it anyway. But in fact, maybe it's just better to save that for, a separate, course walkthrough where we just, find a course on computer architecture. Maybe, I've already, gone through the NAND to Tetris course, so I wouldn't want to repeat that, but maybe in a future video series, I might, pick up some, more in-depth lessons on computer architecture. So, okay, we'll just follow this course and go through chapter 5, section 1, skipping the rest and maybe just diving deeper and more dedicated into the topics of low-level architecture in a future video series. So, okay. So we're going to talk about von Neumann and his computer architecture, right? All computers today are based on the von Neumann architecture. And it basically is just, when we talk about von Neumann architecture, von Neumann was a mathematician and computer scientist. And sort of came up with all these concepts of having memory that you can read and write to, and having a processor that does its own sort of dedicated set of functions. Anyway, just to get, proceed through the text, right? So computer architecture may refer to all of the hardware level of the computer, just anything having to do with the mechanical components, as opposed to, say, the software. However, it's often used to refer to the design and implementation of the digital processor part, right? The part that is actually doing the computations. And that's what we focus on here. Right, so operations are computed on a processor clock cycle, and so that means that there are effectively these electrical pulses that, sort of pulse through the hardware of your computer, and with every pulse, a round, all of the processors perform a single round of computations. This takes a certain amount of time, and then it sends out these pulses on regular intervals. And because they are sort of regular intervals, you can kind of set a clock, right? You can build a clock out of the timing of the pulses, so we call them processor clock cycles. And so this seems to be describing RISC, which is reduced instruction set something. What's that final C? Reduced instruction set computer. Okay, C for computer, of course. Whereas CISC, I guess, is complex instruction set computer. I'm not sure we have a full theory of why this is the case, but lately, as of recording this video, RISC architectures seem like they just perform faster and better. And so I am particularly, and they're also reduced, right? The number of things that you have to know about a RISC system is smaller than what you have to know about a CISC system. And so, both on the designer side and on the user side, they just seem better. I don't have a theory about why they are better. I mean, we could try to sort of BS some philosophy about why, simpler sets of instructions tend to perform better. But rather than do that, probably it's just better to accept the empirical data until things change. So I am more interested in RISC, and so maybe in a future video series, I'll want to sort of investigate RISC specifically. Although I should note that a lot of the the x86, which is the most popular, especially in retail computer systems, hardware, that is not a RISC system, and it's the most popular. So there are good reasons. I think later in this course we are actually going to be learning about the x86, which is more like a CISC system. So I guess we're gonna, in this series, we're gonna learn about CISC, but that's fine. So anyway. But so this is, I guess, a description of RISC, and then in contrast in CISC, rather than using several instructions to implement high-level functionality, many high-level functions are given their own dedicated instruction, basically, so that, rather than having to build it from components, a single call performs that job. It could be that a single CISC instruction performs like a RISC instruction, just on basically a single pulse of the processor clock, although it might instead take several processor clock cycles to execute. And so RISC seems to basically have an instruction, like each of its instructions takes a single pulse of the processor to perform. So if something takes several clock cycles, then RISC would need at least that many instructions for each of the clock cycles. Here's a general history of RISC and CISC. I'm not sure we need to get into the details there. All of these are various instances or systems built in a von Neumann architecture model. Which, again, the von Neumann architecture model basically just means the whole system of having memory and a processor and other components, but just basically the sort of hardware organization that all modern computers, all modern computers use. Programs themselves are data, so that's maybe distinctive of von Neumann models that don't necessarily have to be true in other computer models. Rather than putting programs directly into the processor, programs are data, they are stored in memory, which is an important innovation. So here we'll look at the origins. When tracing the ancestry of modern computing architecture, it's tempting to consider that modern computers are part of a linear chain of successive transmutations, with each machine simply an improvement of the one that previously existed. While this view of inherited improvements in computer design may hold true for certain classes of architecture, consider the iterative improvements of the iPhone, the root of the architectural tree is much less defined. From the 1700s to the early 1900s, mathematicians served as the first human computers for calculations related. Basically, there was a period of time where when you talked about a computer, what you meant was a collection of people doing simple computations, say on, with pencil and paper or something like that. It was menial labor, basically. The first general-purpose digital computer, the analytical engine, was designed by Charles Babbage. It was an extension of his original invention, the difference engine, a mechanical calculator. If you've never seen these mechanical calculators, I wonder if they have a picture. I guess they don't have a picture of one here, but they are a very interesting thing. I think maybe even Leibniz and certain other people very long ago made just these things that were purely, physical metal gears, interlocking gears with pedals and they're very heavy, they're I don't know how heavy, 50 pounds or something like that. And to press the number input to your calculator, there were these big, heavy, stiff metal levers that you really have to push hard down in order to operate these mechanical computers that existed. So very interesting, right? They had these computers just for, calculators, just adding machines and so on. Very interesting. But yeah, so I guess that is we inherit much from that. Also, very interesting that the physical construction of modern computing was basically a straight line out of the construction and design of textile looms. So that's an interesting portion of the history that I would love to know more about. But anyway, Ada Lovelace was the very first person to develop a computer program and to publish an algorithm that could be computed using the analytical engine. She was very aware of the general purpose nature of the analytical engine, because the analytical engine was only partially built. Not sure what that means, but okay. Oh, interesting. And so this was largely forgotten and reinvented later. Okay. Right, so then we had this later innovation of Claude Shannon, often regarded as the progenitor of information theory. Maybe one day I'll do a video series on information theory, something that I've been meaning to learn. He was building upon George Boole, from whom the Boolean values are named. From this we get binary computing, the future of digital circuit design. There were many early female programming pioneers worth appreciating. Yeah, I think one of the ways I dimly recall, I can't remember where I heard about this, but I seem to recall hearing that like computing was, very, more than most other things, regarded as, somewhat equal parity between the men and women who participated in it, up until, I think, if I recall this correctly, when computers started being sold as video game, sort of carrier, right? Like why would you get a computer to have a video game? And a lot of the early marketing, targeted these video game systems to young boys. That it was exciting, I guess, like lots of violence in the video games, and and then sort of like the computer being a video game thing, and also something that you could program. I guess somehow those two things went together, and that sort of really created a strong sense in people's imagination that somehow computing was a more male rather than female thing. So unfortunate. Anyway, discussion of the rise of computer architecture is not possible in this book. Okay. The Turing machine, right. So Alan Turing conceived of basically today's conceptual scheme of what a computer is. The Turing machine is the conceptual scheme of just what a computer is. It is a mathematical concept. It cannot be implemented in hardware truly because it requires infinite memory, and all computers have finite memory. But up to that little detail or limitation, modern computers are implementations of these abstract Turing machines. By construing computation as this kind of mathematical concept, we were then able to prove mathematical theorems about it, such as there cannot exist a solution to the decision problem, which, to know what that means, if you don't know already, you'd want to take like a course in theory of computation or something like that. But basically what it means is that there are some things that no computer could ever do. Basically. And one of the things that no computer could ever do is to decide this thing called the decision problem that maybe we don't want to get into just now. Related is the halting problem, right? There are several problems that turn out to be undecidable by any computer, right? Like cannot be computed by any computer. And there's some details here that maybe, again, are kind of best left to a course in theory of computation, but we'll just kind of understand that Turing created a mathematical conceptual scheme for understanding computation, and with it was able to help design and understand features of computers. Of course, there's this further history related, but not exactly the same, in which he participated in the cracking of codes in World War II. Very, very valuable person. Yeah, there's more information here about World War II and cryptography. American innovations, I guess more American engineers and innovations in the field of computing, especially as they applied to World War II. Grace Hopper, very important foundational figure in especially U.S. advancement of computing science. Developed the first high-level and machine-independent programming language, COBOL. I didn't know COBOL was the first and its compiler. Okay, very cool. Oh, wow. The ENIAC programmers were 6 women. Very neat. Great deal of autonomy in their task, given writing diagrams of ENIAC. The ENIAC programmers also developed the idea of algorithmic flowcharts. Okay, nice, yeah. We use those all the time today. And invented subroutines and nesting. Geez, how did anybody do anything without subroutines and nesting? Well, very foundational contributions. Okay, so I guess von Neumann, in the sort of like the earliest thing that we could identify as his innovative idea, was in a first draft of a report on the EDVAC, which was an update to the ENIAC. It was binary instead of decimal. I cannot imagine how we could have made decimal computers. That sounds, just from a design standpoint, unmanageable. So great that we eventually got binary, but kind of wild that took any amount of time to figure out. But okay. This was a general purpose computer designed to run any program. I thought that's what Babbage made. I guess it was not fully completed. So what is von Neumann's architecture just the first fully completed one? I don't know. I guess, oh, right. But I guess maybe the important innovation is that programs are data. Maybe that did not exist until von Neumann. Right. So I guess, yeah, that seems to be the innovation here, is that programs are data. Yeah, Turing described a similar machine. I mean, but Turing had the concept of a universal Turing computer. Now, just to say briefly what that is basic. Now, this is in his mathematical model rather than in like a hardware model, so maybe that's the difference. But Turing had the concept of programs are data, and, basically in the concept of a universal Turing machine, another Turing machine's instructions would be fed to the universal Turing machine as data on a memory tape. So, how innovative, I guess, is the innovation of von Neumann to take that idea and put it into a physical device? Is that more of an engineering accomplishment? I'm not sure. Anyway. Oh, interesting. Von Neumann is the inventor of merge sort. That's pretty cool. That's like one of the most important sorting algorithms in existence. Okay, so I guess this was mostly, a history lesson with a little bit of concept. I guess more than a little bit, but okay. So the end of chapter 5, section 5.1, and moving on to chapter 6 next time.